All right. Hello, everybody. Welcome to the next subsection here on topic 10. Okay, so in the previous subtopic 10.3, I talked about the differences between the concept of reaction time and response time. And we talked about things like simple and choice reaction time and how those factor in and how we need things like thinking time, and so this is all about breaking down mathematically so we can predict in this subtopic how fast humans will react to things. Ultimately, we're going to also 10.5, we're going to talk about movement time. So this is reaction time and then movement time. We put those two together, we get overall response time. Okay, so going back to that concept of reaction time, and do we have simple reaction time where there's only one possible course of action, like if the brake lights in front of me turn on, I'm going to step on the brake. One course of action versus I may choose among several possible courses of action. That's choice reaction time. And we can quantify how much information somebody has to consider and process, and that will factor into how long it takes them to make these sorts of reaction decisions. So the next question we have is, how do we measure information in a quantifiable sense? And the answer to that is in bits. Okay, so in the same ones and zeros that are used for machine memory, machine language, this is a memory storage that can have two possible states, 0 or 1, or off or on, for example. And so one storage space, which can either be yes or no, off or on, 1 or 0, two possible states, we call those bits. Okay, so what we're quantifying in information is how many different possible states there are, and that's going to factor into how much information that we would gain by learning a certain state or coming to a certain conclusion in choosing from several different states. So just to kind of get you in the right mindset for how this works, I'd like to say, there's two possible states in a storage unit of a bit. And again, I said 1 or 0, on or off, whatever. Another one is to say an answer to a yes or no question. Okay, so in the same way that I can represent, this is binary code here on the right in this table, and the decimal integer, or the base 10 symbol that goes with that integer, and this is how they can be represented. So if you don't know how this works, come join me in office hours. I'll talk through binary code with you. But what you see here is a unique code that goes with every one of these 8 possible states, 8 different system states. And I can uniquely represent each of those states with 4 bits. So if I'm given 4 2-state storage entities, I can represent everything from 0 to 7. Also, so now how do we translate this to humans processing information for reaction and response time? It's like, do I consider this option, yes or no? Do I consider this option, yes or no? Do I consider this group of options, yes or no? And so you'll see there's also this 2-state sort of coding that you can do with decisions. And so if you think of, the minimum number of yes or no questions I might have to ask, where if I get the answers, I will know the fullness of the message. Okay, so I'll show you what that looks like here. So for example, if I asked you, please think of a number between 1 and 8. And I will tell you that because of the way that that bits of information work, and assuming there are only 8 possible states, I can deduce what that number is within 3 questions, guaranteed. Okay, or not within, but in 3. 3 questions or less. Okay, so first question. So think of what that is. Go ahead at home, and I'm going to get it. And first question I would ask is your number, remember I can only ask yes or no questions, that's 1 bit. 1 bit is the answer to 1 yes, no question. So I can say, is your number 1 through 4? And your answer is not, yeah, it's 1 or yeah, it's 3. It's yes or no. So if it's in that range, you'd say yes. If it's not in that range, you'd say no. In either case, with one question, I've reduced the amount of possible states of the system in half. Okay. So with one bit of information, I know you're either in the first 4 or in the last 4 because of how I asked that question. Now, let's say you said yes. My number is 1 through 4. It's one of those in there. It's one of those 4. Then I would say, okay, well, is it 1 or 2? You say no. Oh, okay. So now with 2 bits of information, I have reduced to, now there's only 2 possible states of the system. It could be, I will ask you one more question, one more bit question. Is your number 3? And yes, it is. Or no, it isn't. And in either case, I've answered the question. If you say no, my number is not 3, then I say, okay, well, I know what it is then. It's 4. It has to be. There's only one state left. So with 3 bits of information, I can deduce the possible states of the world from 8 possible states. It's equally likely you could have chosen any one of those numbers, 1 through 8. I asked 3 questions. I got answers to them. And I deduced which of those 8 is your chosen number with 3 bits of information. It took me 3 bits of information to get there. Or alternatively, you could say, if I were to learn what your favorite number between 1 and 8 was, if you told me, yeah, my number is 7, then I would have just gained 3 bits of information in you communicating that to me. So we have to think about how much information is coming in, because this is going to affect processing time, and it's ultimately going to affect reaction and movement time. There you go. So if you just learned it, like if I ask you, what is your number? Just tell me. Well, it's 7. Okay, I've just gained 3 bits of information. Okay, so now we get mathy, right? So with that sort of concept in mind, yes or no questions, now we get to quantify the aspects of a decision. So if I'm going to react to something, it takes me longer to react. Remember, react versus respond. React is the very first instance where you start to see the initiation of a motor response. Okay, the amount of time from time equals 0 to reaction time depends on the probability of the outcomes that you're looking at. Okay, so I'll give an example here in a moment, but if you have something that is very likely to occur and then it does occur, you actually haven't learned very much. You haven't gained all that much information. If something very unlikely occurs, it actually carries quite a bit of information. Oh, I didn't expect that. So now I've gained more information by observing that occurrence. And the way this breaks down, and this is the equation that you will use, H, so just like with the illumination topics, they choose variable constants that are difficult to defend because this represents information, which doesn't start with an H. But we're going to use an H for whatever reason. It is commonly used, when describing this theory. So information quantification is going to be, the information in the signal, at least the S works, right, in the signal. That is going to be the log base 2. We've already talked about log base 10. We use that for the hearing and noise topics, so don't get mixed up. Log base 2 now, of the inverse of the probability of a given outcome. So outcome I, what is the information gained if I observe outcome I? Well, I say the inverse of that probability and take the log base 2 of it. Okay. Now, the way this works out is when let's say I've got several things that are equally likely to occur, the term equiprobable. Okay, equiprobable, you should know that. If they are all equally likely to occur, I've got a 25% chance of each of these outcomes, let's say. Then all of these, this equation sort of simplifies, and you end up with, for any outcome, if my outcome is 25% likely to be yellow, 25% likely to be green, then if all of these are equally likely to occur, then my probability is 1 divided by n. There are 4 states here, so it's 25%. Right? That's obvious for all I. So it's 25% for anything occurring. There's 4 possible outcomes. And when you do the math here, you simplify it, you end up getting log base 2 of n. So I always showed this equation after I showed the full version. Don't get confused. This equation will work every time. In the special case where there are equal likelihoods of outcomes, equal probable, all of these have equal likelihood. If they're not all equal, don't use this, okay? If one of them is different from the others, don't use this simplification. But it does make things easy if you say, hey, give me a number between 1 and 8, and you assume each of those numbers is equally likely to be spoken, then you can take the shortcut and say, okay, I just learned log base 2 of 8, which is 3 bits. Does that sound familiar? All right, so that's exactly what we got to here. 3 bits, okay. All right, so again, that's the approximation. This is the full version, use that one. But so far we're just, yeah. Don't forget, if there's a couple of tricks you can use here. If log base 2 is, if you're using your old Casio keyboard or something, calculator, this trick works pretty well for converting logarithms. So log base 2 of x is equal to log base 10 of x divided by log base 10 of 2. Also, we have Excel, perfectly viable for your assignments and exams in this course. I would suggest making use and familiarity with the log function there. All right. Good, here we go, equiprobable. So again, the special case, but look, I'm gonna leave this one here because this is the equation we wanna use. We can always use this equation, the full version of the equation. All right, so if I think, Ferris gives a quiz and there's a true false question, and man, he words it so perfectly, it's really difficult to tell which one, I didn't read the material, but if I'm gonna take a guess, I'd say, man, it's just 50-50. Each of those questions are written so well. I don't know, true or false, I can't tell. 50-50, okay. So let's say whatever happens, you answered the question, you don't know if you got it right or not. You find out after the exam, oh, actually the answer was true, or actually the answer was false. Either Ferris tells you or you see the grades or whatever. So equally likely outcome, 50%. If I use the full version of the equation, it does simplify to log base 2 of n, with n 2 possible states. So if I learned the answer was true, and I'd say, okay, it was a 50-50 before I knew that, then I would have just gained 1 bit of information, okay? 1 yes or no question. Is the answer true? And you either tell me yes or no, and then I know true or false was the true state of the system. All right, let's say I've got 8 barbecue places in College Station and Bryan that I would say are top notch. They're all rated 5 stars, all right at the top. They're equally loved. Now, tell me which one is your favorite. And if you tell me, oh, it's Fargo's, or, I don't know if these are in COVID times, all my favorite barbecue restaurants have changed names or gone under, unfortunately. But let's say I did learn it's Fargo's. That's your favorite. I will have just earned 8 bits of information, or I will have processed, I should say. I'm sorry, not 8, 3 bits. So reducing from 8 possible states of the world, any of these 8 could be your favorite, to no, it's this one exactly. Of the 8 states, I've gained 3 bits of information. Okay, so again, I could get there by asking questions just like this. I could say, is your favorite, one of these 4, yes or no? And if yes, now I've reduced it by half. If no, I've reduced it by half, right? Okay. All right, there we go, 3 bits, right. Shuffle a deck of cards, assume it's well shuffled, draw 1 card. And now I don't know what it is, and then I look at it. I have now gained 5.7 bits of information by looking at that card, because it was unknown. It could be any one of 52 different states, to no, now it is only one of 1 state. And so I've reduced the uncertainty from 52 to 1. In order to do that, I would have to ask 5.7 yes or no questions. So, this is, of course, illustrating that these are not always whole numbers. In fact, most of the time, they're not whole numbers. But conceptually, it's difficult to sort of explain how do you ask somebody 0.7 of a yes/no question. That, you know, that analogy doesn't work anymore. But you can, if you think of information as reducing the amount of uncertainty in the world, you know, in your, like, learning the truth amidst several possibilities, you're gaining a certain amount of information. This equation, or actually more properly, this full equation will tell you how much information you've gained. All right, so if I have unequal probabilities, it makes a little more sense to use this equation. So I'm pretty sure, you know, Ferris, this one, I think the answer to this one is true. I'm going to guess true. I'd say I'm 75% on that. Okay, well, then you find out, oh, it is true. Okay, well, I didn't gain that much information because I already had a pretty good inkling that it was true. So I'm not surprised. I also haven't learned additionally that much more. 0.4 bits. Okay, well, what if I find out, oh no, I was wrong, the answer is false? Well, I'm actually gaining more information in this case. So me being right or wrong isn't the answer here. Like in what I wrote on the exam, that's irrelevant. That was just me doing the best I could at that time. Now I've learned what the true answer, sorry, it's hard to say with a true or false exam. Now I've learned what the intended, what Ferris wrote the answer to be. And we learned that it's true. I didn't learn that much. Oh, but we learned it's false. If we learn that, I've actually gained more information, right? So, and it's again because the probability of this outcome, before you learned of that outcome, the probability of it was lower. And so when less likely things do get observed, they tend to carry more information. Rare events carry more information. So here's my, you know, illustration if you want to talk about the weather. Okay, that's weather's a good example for talking about an information process, because we can all in the morning look at the you know, the weather, you know, what's expected for the day, and maybe it's, you know, Texas and it says sunny like every day, or wow, it's an unusual, you know, rainy day, or whatever it is. But let's say in the morning I get this forecast and it says, oh, it's going to rain all day. So I think, all right, I better prepare for the rain. I better bring my umbrella, whatever. I better wear my, you know, shoes that can handle rain. Or if I woke up in the morning and I saw this forecast, and it's okay, sunny day, whatever. If indeed I walk outside and I get rained on, if I kind of expected rain, I didn't gain that much more information. If I didn't expect rain, if I thought, oh, rain is very low likelihood, and it did occur, this rarer occurrence, this less common occurrence, will carry more information. I will gain more information as an information processor if something rarer happens. So translate this now to making a decision about, you know, I'm playing a trivia game, you know, and I have to answer as quickly as I possibly can. And you can imagine how, like, you know, when you have more unusual things to consider, they take longer to process. They certainly take longer to react to if those end up being the correct answer. And you'll see how that works down. So far, we're still just talking about quantifying information. We have yet to get to the, okay, and with this much information, this is how long it takes you to react. All right. Typically, when we're talking about, hey, well, how much information is coming in this outcome, right? We can either talk about it like, I got the answer key and I observed what the answer to that question was. And that would be that'd be appropriate for, like, you know, how much did you learn after the fact? But most of the time, if you're making a decision, you actually are looking at, I need to process the potential probability of everything here and make a decision based on having processed everything. So it's not just, oh, I'm going to, you know, true or false. I'm going to guess whatever it is and find out if I'm right later. You have to kind of consider, well, what if it was true? Then what? Okay, what if it was false? Then what? And then you kind of make your decision from there. So we talk about the expected information carried by a certain event. So, like, for example, here, I may have this knowledge before I walk outside. I may have this knowledge before I walk outside. When I walk outside, the rain is going to hit me on the head. So at that moment, I have gained some amount of information. but it's either not that much or it's a lot, okay? But before I go outside, let's say I'm just in this stage here, and I want to know, okay, I got to make a decision about whether or not I'm going to take my umbrella. And so, you know, there's a very high likelihood of it being rainy, but there is this chance of it not being rainy, and I have to consider both of these. And so what I actually end up doing is you come up with like an expected value sort of the information that will be gained when you walk outside. So that's this, okay? H again for information, and the average information gained. And look at this, it's literally, it's this equation right here, but we're going to do a sum across all of the possible states I and multiply it by the probability of that I. So I've just added this Riemann sum and multiplying by the probability there. And this, I think you'll see how this works out mathematically pretty quickly, but this is basically calculating just like expected value. If I flip a coin, you know, heads you get 10 bucks, tails you get 0. You'd say, well, 10 times 50% plus 0 times 50%, I have expected value of $5 in you know, before I flip it, I expect $5 per flip. Similarly, before you observe it, you can expect H average information content in observing the outcome of the unknown state of the system, okay? So how much do I gain by learning, by getting the answer key and knowing if it was true or false in that one example? And assume again, it was 75% likely to be true. Well, now I'd say it's 75% likely to gain 4 bits of information, and I'm 25% likely to gain 2 bits of information. And again, that comes from right here, right? So the information that I would gain if it is true, 0.4. And the probability of it being true is 0.75, right? So that's where 0.75, 0.4 come from. So I'm multiplying the probability by the information content in that event outcome. And I add them together because I'm doing the expected, you know, the average information. I have to have all of the states represented. And now I get 0.8 bits. Now we can compare this with when they were equiprobable. Remember when it was like 50-50 true or false? So this is interesting because what this shows is on average, I gain the most information on average when events are closer to being equally likely. When events are equiprobable, you have the maximum information expected per gaining of you know, per observing that outcome. Okay, so 1 bit being the maximum value there. That'd be a good question for a midterm, by the way, or a final exam. Would be something about let's maximize, let's get the absolute highest expected information content. The answer will be, well, if they're equally likely to, if all of the possible outcomes are equally likely to occur, you are maximizing the information, the average information gained per observance. When you get to the math, the fun part for your assignment, I would recommend working in Excel because you're going to get mathy with it. So what I'm representing here is potentially, let's say there are 4 possible outcomes, outcome A, B, C, and D, and these are the probabilities of their occurrence. So however I know that information, when I do problems, I'm going to give you that information. Now you can do all the Excel work to come up with, well, what's the inverse of that probability? What's the log base 2? What is, you know, multiply the probability times the log base 2, right? Or the information content here, and boom. So that's where I've summed everything together. I get 1.75 bits is my expected information gained on average. Okay, so here is where we get to calculate how long it takes to process that information. So the mathematical equation that goes with reaction time, so RT, I forgot to put reaction time. Don't confuse reaction time and response time. Oh, I'm going to confuse things a little bit here, but the Hick-Hyman Law, 2 scientists, one named Hick, one named Hyman, came together and said, we have this relationship between the amount of information that needs to be processed before a reaction can occur and the amount of time that it takes a human to respond. And here we go, RT. Now I'm going to just say RT for now because this next point here kind of clarifies why. For the most part, RT is going to be reaction time. So when we say, how long did it take somebody to react versus respond, you're going to need to distinguish those two. Reaction time, reaction time is linearly related to the logarithm of, or basically to the amount of information processed, right? So, if you have the x-axis here in bits, h of s, and response time, or reaction time, you can define it by this nice linear line, y plus b times the amount of information in the signal. A and B are empirical constants. However, they're going to look very familiar, at least A is, based on what we were talking about in section 10.3 about reacting to visual stimuli, okay? So A is going to be our simple reaction time. Remember, simple versus choice reaction time. So the constant is basically, if you're responding as fast as you can, then A is as fast as you possibly can respond, your simple reaction time. B times however much information you need to process. So if there are 0 bits of information to process, your reaction time is equal to A. And so that's where we say, okay, well, this is why we distinguish simple and choice reaction time. B, think of it as the processing time per bit of information. This is a good way to sort of think about, well, how, what is the bandwidth of our processors here? Now, I've got this disclaimer down here. RT can apply to either reaction time or response time. The way it does that is by changing these empirical constants. So I really like just using this for reaction time, because then I can relate A, simple reaction time, and then the processing, that's our thinking time per bit of information. And so if we just stick with the reaction time, I think it works a little better for it. And that's all I'm going to do for the purpose of this class. But you should know this law is applicable to response time. You just would have a different value of A. So rather than your simple reaction time, it would be simple response time. So you're still factoring in all the thinking time times, information content, but the constants basically change. All right. All right. So from here on, RT is going to be reaction time. I will do my best to not mix those up. Okay. So here's the equation again: A plus B times H of S. We know how to calculate H of S, or often H average, the average information content. Yep, the inverse of bandwidth, if you want to think of B here. So, and we think about, how much data am I getting per unit time in terms of what I'm paying for my internet connection, for example. It's the same sort of math here. It's just the inverse of that. So, if I had a 1 gigabyte per second processor, the value of B would be that. And I could plug it in, right? So if I had an AI brain, for example. All right. And then empirical for reaction time, 0.15 seconds for reacting to a visual cue. Really cool, because that is what we calculated with Derek Jeter in terms of how much time it would take him to process that incoming baseball, if you'll remember. So 150 milliseconds, that was the time that we had highlighted there. So that comes back into play here. 150 milliseconds becomes our simple reaction time in this equation. 0.13, this is what I want you to use for this class. But know that this is also an empirically derived number. To get this number exactly right, you probably have to collect a bunch of data and then determine, model to determine what this value is. All right, here's our example. We've got a skunk in the road. We want to know, what do we do about it? So this is, I like to start to put things together here from other topics where, for example, we talked about how large certain visual items need to be in order to be seen from a certain distance. And now we can say, well, how long is it going to take me to react to something that is a certain distance away, and considering all the things I might do. So you can think of a roadway and what should the speed limit on this road be? One of the questions should be, well, how far away can a human see? And then make sure that they're not traveling so fast that they don't have enough time to respond according to these models, before they decide what to do about something they may see in the road, right? So, all right, we got a skunk. Right? There's a skunk in the road. Let's say I am driving over I crest a hill. I see the skunk. Time zero, time equals 0. The clock is started. Now I consider 4 possible courses of action. Okay, let's assume all 4 of these I'm equally likely to choose. That's a huge assumption, but just to make, for this simpler example, it's equally likely that I'll swerve left, swerve right, hit the brakes, or speed up. Now that's probably not a good one, but let's just say these are the 4 possible outcomes that I could do. Or you could say do nothing. Maybe the 4th one is a conscious do nothing and just run over the skunk. Probably not a good idea, but it is an option. So what is the base case? And I use those key terms, expected or average reaction time. So I could say, well, what is the reaction time if you swerve right? Or what is the reaction time if you swerve left? I'm not asking that. I'm saying consider all of these and what is the expected, could be any of these that are ultimately chosen, or what is the average reaction time in this context? Okay. So 4 equally likely. So we can use our simplified version. Again, remember, you can use the full version also. I've just simplified it to log base 2 of n because I know it will work when they're equiprobable, right? So plug them in here. I know I've got 2 bits of information to process in deciding which of these 4 things I'm going to do. And you want to break it down into yes, no questions again, right? 2 bits of information. I could ask, are you going to swerve? Yes or no? And if you say yes, then I could say, are you going to swerve left? Yes or no? And so I could reduce these 4 states of the world to 1 with 2 questions, 2 yes or no questions. I've gained 2 bits of information, right? All right, so we're using these constants. We're using the ones that Ferris told us to use, but again, we remember where that 0.15 comes from. And so we remember, again, reaction time is me just beginning to lift my foot off of the accelerator, the very first observable instance of a responding activity. Okay, so split second that foot lifts. That's our reaction time. And what this tells us is it'll take about 0.41 seconds. Okay, so I'm thinking about 4 possible things. By the time I decide what I'm going to do, the average amount of time before my foot lifts up, 0.41 seconds. All right, now let's say, well, now we have slightly different probabilities. Let's say most of the time I swerve left if I see anything for whatever reason. So that's 50% of the time I just, anything's in the road, my go-to thing is swerve left, I guess. And so if then you believe me there, then you can say these are my probabilities for each of the 4 possible outcomes. Fortunately, least likely that I'll just blast right over that poor skunk. But now I'm going to use the full version of this equation, and I'm going to do the multiplying each probability by the information content and summing them all together. So that looks like this. By the way, I will expect to see this kind of math in your homework and exam. So you'll want to be used to working through these iterations and summing everything up and getting a number that hopefully seems like it makes sense. So one quick, easy mental check. You remember that the maximum information content comes when there are equally likely outcomes. For 4 equally likely outcomes, log base 2, 2 bits. So what you know here is if there's 4 outcomes, you can't get any higher. There isn't any more information that might be processed than this amount, okay? At least if you're talking about the average information content. So 2 bits is gonna be you should not have a value higher than 2 bits, but it should be sort of comparable to 2 bits. So 1.685 bits, that makes sense. It's gonna be less than 2 because it's not equally, equiprobable, which would then lead to that distribution. But we have somewhere between 1 and 2 yes and no questions to get the answer here. All right, so plug those guys in. Now we'll look at 0.37 seconds. So what happened there? Because at 0.41 seconds, when they were equally likely, I actually speed up when they're not likely. So how does that work? And again, this comes down to the fact that when you have likelihoods higher than equal likelihoods for some of your outcomes, you're much more likely to observe those outcomes, and you're more likely, therefore, to have a leg up on responding to them. So, basically, when something is more expected and it does occur, you process less information with that, right? So this shorter reaction time actually kind of reflects that I am relying a little bit more so on the higher likelihood of one of the outcomes. So I don't have to, it's kind of like I can get away with mostly thinking about the first one and the second option here. And so in a way, this is at least how I rationalize this difference here. So when you have something that's more likely to occur, you don't have to process as much information when it does occur. And therefore you have potentially faster reactions here. Okay, now these are idealized. 0.37 seconds as a reaction is probably not going to be observed in a real case unless a very controlled condition. This is ideal. This is like everybody is driving all the time looking for a potential skunk. Like it doesn't really reflect humans in a if they're not suspecting something, if they're just kind of going about their everyday lives. So subtopic 10.6, we're on 10.4 right now. 10.6 is going to talk a little bit about the differences between these predicted models, these predictive models that generate these, these really idealized reaction times, and then what's maybe closer to what's observed in the real world. But for now, I hope you can see this is how I want you to calculate your reaction time metrics. So on average, when there are more extreme probabilities, much more likely that this one thing will occur, decisions are made faster, choices are made faster, reactions are faster. Okay, now, often when we start to react to something, it isn't usually it's often not a one and done sort of cognitive event. I gain everything that I need to know, I make the decision, and I act on it. Humans do a little more of a continuous process where they will begin a response and they may adapt on that. So what I'll call are like sequential choice reaction time. So let's say the first thing I need to do is make a decision about what is that thing in the road? Is it a skunk or a blown out tire? I can calculate how long it will take to make that decision and begin to react to it. So now at that point in time, now I'm going to make a decision about, okay, well, based on the surroundings, what is an appropriate course of action? So first, is it a skunk or not? Because that matters, because it will give me my potential, my potential courses of action. So if it is a skunk, then 4 courses of action. If it's a tire, there may be different courses of action, but those don't get considered until I first identify is that a skunk or a tire. All right, so what we do then is we calculate the reaction time just to realizing what the thing is. Is it a skunk or a tire tread? Okay, 2 equiprobable choices, let's say. And so, when we do that, we have, 1 yes or no question. We have 1 bit of information. We plug them into our Hick-Hyman Law equation using the same constants. And now I get 0.28 seconds. So it's going to take me 0.28 seconds to get to the point from time equals 0, where I first started to see something, to 0.28 seconds later, I'm going to know, is that a skunk or is that a tire tread? I know that much so far. Now I need to decide what I'm going to do. Now I've got these 4 courses of action I can take, okay? So what you do then is you take this 0.28, and this becomes the new value for the A constant in the Hick-Hyman law, right? So now A becomes 0.28 because A is basically how long until thinking time, right? How long until you get to the point where you're thinking about your options and then activating them. And so 0.28 is how long it took me to get to the thinking time of about my 4 options. So then 0.28 goes there, 0.13. I multiplied by the expected information gained in that, that comes from this one, 1.685 bits, the information average and the expected information. And there we go, plug it all in. Now I get 0.50 seconds. So you can chain these things together, sequential sorts of cognitive activities, and it will work with the Hick-Hyman law as well. All right, that's it for this topic. Now, again, we just talked about reaction times and how to predict reaction times. We haven't even started moving yet. Movement times are in the next subtopic. Okay, thanks.